Today we'll be looking at increasing and decreasing functions. So to begin looking at our increasing and decreasing functions, let's look at the graph of a generic function y equals f at x. So I've drawn here a generic function in our pink, and I've labeled a couple points, a, b, a1, and b1. So you'll notice in our first part here we have a and b. Now looking at our tangent line, so looking at it between a and b, if we draw our tangent line there, you'll notice that our tangent line is positive, and therefore we know that our f prime of x would be greater than 0. So now if we were to look on our other side where A1 and B1, and we do our tangent here, we notice that our f prime of x would be less than 0. And that is just because of the fact that we have a decreasing slope. So we can fill in here, if f prime of x is positive, then the tangent line slopes upwards. And if the tangent line is negative, then if f prime of x is negative, then the tangent line slopes downwards. So note here, for any a less than b on an interval, we say that the function is increasing on the interval if f at a is less than f at b. Similarly, if is decreasing on the interval, then we say that f at a is greater than f at b. So now let's go ahead and look at the theorem here. So our theorem, the increasing, decreasing test for a continuous or differentiable function. 1. If f prime of x is positive on the interval, then f at x is increasing on the interval. And if f prime of x is negative on the interval, then f at x is decreasing on that interval. So note here, if f prime of x is equal to 0, when f at x switches from increasing to decreasing. So that is obvious because when we're trying to look at our tangent lines and we want to look at when we have an extrema, so a max or min, we know that if we set our derivative equal to 0, we know that's going to be a max or min. So example 2 here, or it's actually example 1, sorry. We want to determine where f at x equals x cubed plus 3x squared minus 2 is increasing and decreasing. So our first step here is to find our derivative. So our f prime of x is actually going to be equal to 3x squared plus 6x. And now, since we know where it's increasing and decreasing, we can find this by setting this equal to 0. So if we set this equal to 0 and factor out a 3x from our right hand side, we're going to be left with x plus 2. So therefore x is going to be equal to 0 and x is going to be equal to negative 2. So these are the two values that we'll be looking at. So now looking at our theorem, the increasing decreasing test for a continuous or differentiable function. If f prime of x is positive on the interval, then f at x is increasing on that interval. And if f prime of x is negative on an interval, then f at x is decreasing on that same interval. And also I'd like you to note that if f prime of x is equal to 0, then f at x is, this happens, when f at x switches from increasing to decreasing and vice versa, which we know that when looking at our extremas in our last unit, we knew we could find the derivative and set it equal to 0 because we knew that our tangent line would be 0 at that point. So in our first example here, we want to determine where f at x equals x cubed plus 3x squared minus 2 is increasing and decreasing. So our first step here is that we need to find the derivative of f at x, which is just equal to 3x squared plus 6x. Next, we're going to set that equal to 0 since we want to know where it's increasing and decreasing. So if we set it equal to 0, we know that that's that point where they're going to be switching. So we set it equal to 0, factor out a 3x on our right hand side to be left with x plus 2. So therefore x is equal to 0 and x is equal to negative 2. So we're going to be looking at those values of x. So at negative 2 and 0, and we're going to look at it on either side. And we're going to concentrate on our f prime of x and our f at x. So f prime of x, if we want to look at a value on the left hand side of negative 3, let's look at the value of negative 3. Sorry, on the left hand side of negative 2, let's look at the value of negative 3. So if we sub in negative 3 into our derivative here, what we're going to get is we're going to get 9 when we expand and simplify this. Therefore, f prime of x is a positive. Since we know from our theorem above, if f prime of x is positive on the interval, then f at x is increasing on that interval. So we know f at x will be increasing. Now if we were to look at a value, say negative 1, between negative 2 and 0, we're going to get that our value is negative. And by the theorem above as well, if f prime of x is negative on the interval, then f at x will be decreasing on that interval. So therefore we know it's decreasing. And any values after 0 for our f prime of x is going to be positive. So therefore we know that that will be increasing as well. So now, if we look at our values at negative 2 and 0 of our function, so f at negative 2, we sub it into our original, negative 2 cubed plus 3 times negative 2 squared minus 2, we're going to get that this is equal to 2. So our value would be at negative 2, 2. And if we looked at it at 0, we're going to get the value of 0, negative 2. Therefore, at x equals negative 2, we have a max, and at 0, we have a min. So if we want a visual of this point here would be negative 2, 2. This point down here would be at 0, negative 2. So this is just a rough sketch, just to give all of us a visual. So you see how our function here is increasing. Then we get to negative 2, and that value, or f prime of x, would be equal to 0. And then we have a decreasing function. We hit 0, and then it goes back increasing. So therefore, f at x is increasing on the intervals where x is less than negative 2 and where x is greater than 0. And f at x is decreasing on that interval from negative 2 is less than x, which is less than 0. So now in our next example, we want to consider the graph of f prime of x, and then we want to graph our f at x. So if we look here, we have our values of negative 4 and 2. So we can use those values when discussing our f prime of x and our f at x, because those are our zeros on our f prime of x. So looking at those values at negative 4 and positive 2, we can create a little graph here, and we're going to look at f prime of x and f at x. So when we do this now, we can see that when we look at our f prime of x, we have our intervals there. So let's first look at our f prime of x is equal to a times x plus 4 times x minus 2. And that just comes from our quadratic formula. We can also take the point of 0, negative 4, sub that in to find what our a value is. And what we're going to get when we expand and simplify is that our a is equal to a half. So therefore our f prime of x is equal to a half times x plus 4 times x minus 2. We can expand this and it would be a half x squared plus x minus 4. So that's just a way that we can get our f prime of x. So we notice here that our f prime of x, as we approach our negative 4, it is positive. And as we pass negative 4 and we go to 2, that value is a negative. And after 2, it is once again positive. So therefore, when we have a positive derivative, we know our f at x would be increasing, negative would be decreasing, and positive once again would be increasing. So therefore I know that I'm going to have a max at negative 4 and a min at negative 2. Now, if we want to know what the actual equation was for our f at x, you could just work backwards. And we know that this would have ended up being x cubed to begin with. So how would I get to a half? I would have 1/6 x cubed. Similarly, I'd have a half x squared minus 4x, and then I'd have a c value. So I won't know my exact values of my y's, I just know that at negative 4 I'm going to have a max, and at 2 I'm going to have a min value. So I'd have something that would be similar to this function here. Now in our last example, for the function defined by f at x equals x cubed plus bx squared plus 12x minus 3, we want to find the values of b that result in f at x increasing for all values of x. So if we know that f at x is increasing for all values of x, we know that f prime of x is greater than or equal to 0. So we also know that if it's increasing, we are going to have a function that looks something similar to this when we take the derivative. So f prime of x would be equal to 3x squared plus 2bx plus 12. And since we know that it needs to be greater than or equal to 0, we can now set our 3x squared plus 2bx plus 12 greater than or equal to 0. So using our discriminant, so something you haven't used in a little while. So using our discriminant, if we had 2 real roots, our b squared minus 4ac would be greater than 0. If we have 1 real root, our b squared minus 4ac would be equal to 0. And no real roots, we'd have b squared minus 4ac is less than 0. And since we know it's increasing for all values of x, we know that we would have no real roots. So we can then set our b squared minus 4ac less than 0. because we know the other ones won't work because we don't have any real roots at all. So looking at that, we need to know what our A, B, and C values are. Our A here we know is going to be 3. Our B is going to be equal to 2b. If that's confusing, you can change that to 2n if that helps. And we know our C is going to be equal to 12. So we can now sub in those values. So 2b squared minus 4 times 3 times 12 is less than 0. So we have 4b squared minus 144 is less than 0. We can factor out a 4 and we're left with b minus 36. That works out really nice because this is a difference of squares. So 4 times b plus 6 and b minus 6 is less than 0. So therefore we know these are our values that we'll be using. So therefore f at x is always increasing for the values of -6 is less than b, which is less than 6. And that's our final answer.